cameras, for example. Like one interesting application would be the auto-driven cars to drive themselves. They have cameras, so use that and then integrate with the mirrors. Definitely, like we can, like everything is becoming smarter. So like,
okay,
we'll have smart mirrors. Man.
Cool. All right, let's thank the speaker again. Move on to the last talk in this session, bringing biometric authentication to smartphone devices. Very cool. CapAuth, presented by Anhong Hu, identifying and differentiating users' handprints on commodity capacitive touchscreens.
Hi, thanks for the introduction. Good afternoon, everyone. My name is Anhong Hu. I'm a PhD student in Carnegie Mellon University Human-Computer Interaction Institute. Today, I'm going to talk about CapAuth, identifying and differentiating user handprints on commodity capacitive touchscreens. This work was done in collaboration with Robert Xiao and Chris Harrison. User identification and differentiation have uses in many application domains, including security, personalization, and co-located multi-user systems. We propose CapAuth, which uses the touchscreen data to recognize users. CapAuth does not require any additional hardware or sensors and can be run on most modern touchscreen devices. Many systems in the literature aim to extract biometric data from the touchscreen. For example, Fiberio uses a large fiber optic plate and a high-resolution camera beneath the surface to capture fingerprints. Handsdown use a diffuse illumination interactive tabletop and hand contours for user differentiation. Carpus use a high-resolution overhead camera to capture the user's back of hand and use that as identifiers. And capacitive fingerprinting uses a special sensor attached to the infrared touch panel to measure the sweat frequency impedance of a user. In contrast with these methods, our approach uses low-resolution commodity capacitive touchscreens found in nearly every smart devices today without requiring user or device augmentation. Most related to our approach, BodyFriend identifies users through different body parts using the touchscreen. For example, the ear, the fist, and hand grips. We extend this with a hand flat pose, which reveals more distinguishing user features and enables higher recognition accuracies. We also run a rigorous study, one that evaluated classification accuracy in real time, how robust accuracy was over a longer period of time, also the moisture resistance, for example, after the user washed their hands. CapAuth uses the capacitive image of the smartphone. Robert previously talked earlier in this session about acquiring the capacitive image from the debugging interface of a smartphone. On our proof of concept implementation on the Nexus 5 smartphone, we modified the Linux kernel to provide access to the 16-bit 15 by 27 resolution capacitive image at 25 frames per second. We selected the hands flat pose for identifying and differentiating users. So the users place their middle finger aligned with the red dot on the screen and keep their fingers aligned with the short edge. This pose produces consistent and reproducible handprints. Here are some sample capacitive images of handprints that was captured from multiple users. As you can see, there are differences between these images. We derive a series of capacitive and geometric features from the capacitive image. We extract the positions of the 4 fingertips and the attached fingers, and then calculate the statistical features of each finger. For example, the length, capacitive weight, width, geometric centroid, and also pairwise distances and angles between the points. We also included raw value of each point, mean values, etc. These features are used to train a support vector machine classifiers using the Wacom machine learning toolkit. To ensure that the users use the correct hand pose, we train a binary classifier to differentiate between correct and incorrect hand poses. CapAuth can perform real-time authentication for a specific user or identification in a group of users. For authentication, we use a binary classifier specific to that user, which distinguish between that user and all other users, and for example, unlock a phone. For identification, we train a multi-class classifier to differentiate between a group of users. Then we want to know how well this technique works. We ran a series of studies to evaluate authentication and identification accuracies, as well as its robustness for moisture change and its performance over time. First, for data collection, we recruited 20 participants, 10 female and 10 male, with a mean age of 26 years old. There were 5 sessions of handprint data collection, each separated by a short break to avoid overfitting to similar hand placement of the hand. For the 4 breaks among the 5 sessions, participants were asked to complete a survey, trace an outline of their hand on the paper, complete another survey, and wash and dry their hands. Participants were asked to place their right hand down onto the screen in a natural way and press the physical volume button located on the side of the phone to record 1 handprint trial. They were asked to lift the hands from the screen between the trials to add variety to the data, and 50 handprints were collected in each session. One special session collected improper hand placement, which we used to train our correct hand placement classifier. In this session only, users were instructed to put their hands on the screen in a way that does not match the on-screen guide. In total, 4 sessions of proper hand placement data were collected, producing 4,000 correct handprint instances, and 1 session of improper hand placement data was collected, producing 1,000 instances. To evaluate the accuracy of hand placement classifier, we ran 1,000 rounds of simulation. In each round, we randomly chose a stratified sample consisting 70% of the proper and improper hand placement data and to form our training set and test it on the remaining 30% of data. And overall accuracy was 99.7%, demonstrating robust rejection of the incorrect hand placement, which is an important pre-check before attempting authentication or identification. To evaluate authentication accuracy, we run 20,000 rounds of simulation. In each round, we label 1 participant as authorized and the remaining as unauthorized. We randomly combine 3 out of the 4 sessions to form our training set and test it on the remaining session. The reason we do this instead of cross-validation is to avoid overfitting of similar placement of the handprint within 1 session and to add variety. Overall, our technique achieved authentication accuracies of 99.6%. More specifically, looking at the confusion matrix, 5.5% of the time, the system falsely rejected that participant, which would prompt the user to try again in real-world applications. And on the other hand, only 0.1% of the time, an unauthorized user was falsely accepted into the system. To evaluate identification accuracies, we run another 1,000 rounds of classification simulation. In each round, we assign each participant in a separate class, and then we randomly combine 3 out of the 4 sessions of each user to form the training set and test it on the remaining session. Overall, our technique achieved identification accuracy of 94% for 20 users. This accuracy is not high enough for identification for a large group, for example, 20 users, so we're wondering whether it might be useful for smaller groups, for example, a family. So we conducted a post hoc experiment simulating family units of size 4. In each of the 1,000 rounds of simulation, we randomly picked 4 out of 20 participants to form a family and to construct an identification classifier for that family. Overall, our technique achieved identification accuracy of 98.2% for a size of 4 groups. As shown in the histogram, more than 40% of the families achieved 100% accuracy, and around 85% of families achieved more than 98% accuracy. In data collection, we asked the users to wash and dry their hands before the last session. This was included to see whether altering the moisture level of their hands could affect the identification accuracy. So for authentication, the accuracy for the session after washing hand had no significant difference from the sessions before washing hand. And for identification, the accuracy for the session after washing hand is slightly worse than the sessions before washing hand, though this is not statistically significant. We were also interested in how CapAuth performed over time. We asked 10 of our participants to return for a follow-up study several days later, with a mean gap of 8 days. Using all the handprint data collected in the previous study, we initialized our smartphone Nexus 5 with participant-specific authentication and identification classifiers. Each participant then collected handprint data following the same procedure as the last study. However, this time, live classification was performed on the phone to gather the results. And the interface was the same as the last study, which provided no graphical feedback to prevent the users from adjusting their hand pose to match the classification result. The new authentication accuracy was 98% compared with 99.6% in the previous offline simulation. And identification accuracy was 96.5% compared with 94% previously. Neither differences was statistically significant, suggesting that CapAuth may be stable over time. For identification, with the 94% accuracy among the 20 users, CapAuth is not well suited for high security applications or user differentiation between a large group of users. However, CapAuth can accurately identify users within small groups at 98.2% accuracy, so it might be used as a simple user differentiation mechanism for shared devices, for example, parental control for a family tablet, or tracking of individual users on a shared tabletop touchscreen. For authentication, 99.6% is reasonably high in a large group of 20 users. CapAuth could be useful as a two-factor authentication method. Finally, one limitation of this technique is its potential susceptibility to environmental effects. For example, in an electrically noisy environment or humid environment, when the phone is grounded to a charger or a proximity to high-power electric devices, or there are raindrops on the phone. So the performance of this technique will improve with the high resolution of capacitive image. And the production of these devices are already in the pipeline. Thanks for your attention.
Two questions. It's me again. Why the touchscreen? You mentioned how important resolution is to you. Why not use the camera?
So the touchscreen controller is already always running for detecting touch. So there are computer vision approaches out there, but those are very expensive. So will drain battery. And this technique can be very low, computational expensive, so it can be potentially integrated into the existing hardware.
It's an interesting point because when we got the debug image from the phone, that actually drained the battery quite a bit. So I was just wondering if you snap one picture at the megapixels that you get from, for instance, the back-facing camera against the the forward. So do you think, because your algorithm, it's all relative, right? Do you think it would transfer over, you could use it based on an image, and then maybe even get better results because you have more resolution?
You mean use the back camera to capture hand?
The front camera, yeah.
So I think using a camera solution, it is very sensitive to for example, lighting conditions, stuff like that. But for the capacitive image, it's actually capturing the biometric data of the user, which is more consistent over time and the environment. So I think that in that sense, it could be better. But since the resolution of the capacitive image is there are companies that are making high resolution capacitive images, so this technique could be better integrated, I think.
All right, fair enough. Anything?
Yes, I can shout it.
So, maybe have you thought about doing some movement with the hand to just make it even more accurate? And say, yeah, you pick the hand, but you make the hand rotating or something like that. I was just browsing a pattern from Google that does doodles. People does doodles to authenticate, and it just came to my mind.
Yeah. I think that's an interesting idea, and also it will work using both the movement and, for example, like a movement password together with a capacitive image. And there is an existing literature called biometric bridge gestures, which uses the hand movement and also the palm to do user authentication. So I think that could be integrated.
All right, let's thank all speakers again.